Well, hello again. This is Terry Sagan, and today we're going to learn about. Well, we're going to go over an example of how to use some of the forces and some of the moments on a very simple uh, beam or bar with a pin joint and a piece of string. So this is the example problem, and you can see it has a bar through AC here. Um, and that bar is 4 feet long. And what I'm going to do is I'm going to say that this is, we'll give that not a letter. This A is 3 feet. This B is 4 feet. And this force, let's give that an F of 6 pounds, 60 pounds of force at one end. The other end is pinned. So we'll figure out what to do with that in a second. And the bar is also supported by a string to load the bar and tie it to the wall. So that's what this B is for. So you have this string that's connecting B to C. Let's see how we can start to solve this. So basically we want to know the reactions at, let's call this A. Then we also want to know the tension in the cable. So how do we do this? Well, first we write our givens. Our givens, well, we already kind of discussed that. So we have A is equal to 3 feet. B is equal to 3 feet. We also know that the F is equal to 60 pounds of force. So what are we trying to find? Well, we're trying to find the tension. Let's call that T. And we're trying to find whatever A is. So the force is at A. You can describe it as A. What I usually do, sometimes I write, instead of A, I would say the force at A. That's just my subscript. You can choose however you want. So first, let's draw an illustration of what this actually looks like. So we're doing a free body diagram. It's the type of illustration to look at and start to analyze this. So we have this bar with these two points here right now. So let's take a look and start labeling these. So first and foremost, we have this string. And that string says that there's a force, this tension here. So you can't push on a rope, or you can't create a moment and bend the CB, or else it wouldn't be. It would be a totally different problem. It's straight, and it only can apply tension to this rope. So that's the first and foremost. So that's called the applied load. Let's take a look at the reactions now. So I'm going to write the reactions in blue. Oh, sorry. Nope, that is the reaction. I'll keep the reactions in red. So another thing is, you notice we took out this pin. So this pin's no more, but we need to replace it with components. Now we can do this. This is one way to do it. There are multiple ways to do this. So we're going to put FAX and then FAY. And what I'm going to also do is I'm going to put now a coordinate system on here. So this usually is our standard X and our Y. And most free body diagrams have them. If not all free body diagrams have to have some sort of X and Y, because it doesn't make sense otherwise. Because I want to know where the origin is. And the origin, I'm putting the origin at this point. I'm putting the origin because a lot of things are going on here. I could put it over here, but it would be fine too. And then what we forgot to do is we forgot to have, or I forgot to, not you, but we forgot to have this load, and this we called F. So where do we start? Well, now we have this free body diagram, and it's if you noticed, I cut a rope and I've only pulled it. I put it in tension. It's not, since it's a string, you know it's not going to be in compression. So I'm pulling away from C. And on this, let's label C. So let's say C. And let's keep it black, the color. So with that, where do we start? What's our plan of action? So our plan of action, eventually we want to find out what T is, FAX and FAY. So we start with what we know. So we know this. We know this force here. So if we take the sum of the forces in the x direction, because there's only 3 equations that we can play around with, and let's write them down. And then we can start to the order. So we have the sum of the forces in the x direction, sum of the forces in the y direction is equal to 0, and then sum of the moments. And you put z there because it's actually, there's a z and that's coming out of the board, and that's also equal to 0. So these are the components of larger set of equations, which we'll have time for in another video. But for right now, these are the equations, these are the general equations you'll see in statics. All right, so first and foremost, which one do we choose to go first? Well, let's take a look and just think through. So if we sum the force in the x direction, we have this force AX, and then we have a component of tension also in the x direction, but we don't know either one. So let's not start there. We can develop the equation, but let's not start there. Furthermore, if we look at the forces in the y direction, we have the force AY. We also have this force here, which is the applied, and we also have the tension in y. So we have forces known, which is good, but we don't know the tension and the FAX. So that's not really going to do us any good. So let's not start there. So we want to start, and this right here is our only best bet. Now, not all the time is this going to work out, but this method will work out for this this particular problem. So where do we want to take the moment about? We could take it anywhere in space. We could take it up here if we want, but let's not start there. So let's continue on. And if we take the moment here, we know that the force goes right through there. So that eliminates that. And we only have this force AY here. That's interesting. So if that's the only force at AY, we can say that that's going to be equal to 0. But we'll leave that time for well, let's do that. I like that. So if we take the sum of the moments about C is equal to 0, and we know this is perpendicular distance, so that is our B, and we can say that B times FAY, the only thing you can do is set that to 0. There's no other moment causing about B to say. So we can satisfy this, and we can say FAY is equal to 0. And in another video, we'll continue on through. This will be a 2-part series.